we are just about to look at this very nice algorithm called the Rete algorithm, which works on something called the Rete Net. And the goal of constructing this Rete Net, as we have mentioned, is to optimize on the work that you have to do during match phase of the cycle of the inference engine cycle, match, resolve, execute. In every cycle we want to do the minimum amount of work for match, and even within a cycle we want to share the match needed by different rules and different patterns. If it can be shared and done only once, we would like to do that, and the Rete algorithm does that very nicely, or the Rete Net implements that very nicely. So, let us get on with this. The basic idea that we want to start with is a general concept used a lot in computer science. These are discrimination trees, and the idea of discrimination trees is to organize data in such a way that finding specific pieces of data becomes faster essentially. Where is the notion of finding for us? Essentially, we are going to say that we have a new working memory element. Remember that we are going to be making only changes into the working memory element, and as an output we would expect changes into the conflict set. So, assume that we have this process going. To be more precise, if you look at this algorithm, look at this diagram again, it says that changes in the working memory result in changes in the conflict set. How does one start? At the very beginning, the working memory is empty to start with. You start your application, which means you load the Rete Net, and the initial working memory you put it at the top, as we will see, put it down the network. So, it will serve as changes, because the first time that you are adding the entire data, it is changing the data, but subsequently all the data that you have entered earlier will remain inside the system, and only the new data that you create will be added to the system. So, this new data that you add to the system, which is the Rete network, needs to go and find which rules it matches. Okay. So, this process of the working memory or data looking for a matching rule is what we are going to try and do this here, and we will use this very common idea used in many areas of computer science, which is called discrimination trees essentially. The basic idea of discrimination trees is to keep distributing the patterns which need to be matched, so that instead of sequentially trying out all patterns, once you have tested for one, let us call it attribute of a pattern, then you have to only look at a smaller segment of the target set essentially. In our case, the target set is patterns in the rules, but you can think of it as the other way around also, that there is a pattern in the rule which is looking for a matching piece of data. So, all patterns with all data, we are just trying to change into that. This, if you take the analogy from the blood vessel network that we were talking about, it is like saying that from the heart you send out blood and it goes all over the body looking for various organs to replenish with oxygen essentially. Anyway, so in computer science, in computing, a popular approach to work with large amounts of data is to use a divide and conquer approach and route the data, or route the query rather, or data token via a sequence of tests. So, the generic diagram of such a discrimination tree looks like this, that you do a test which we call as test 0, then based on the value of the test 0, it will go down to one of these branches below that, either here or here or here or somewhere, and then it will do another test, and again it will get distributed and so on. So, I am sure you are familiar with this kind of trees. The most common of them are binary search trees, with all students start with essentially when they look at data structures. So, binary search trees and B trees and decision trees, if you have looked at machine learning, KD trees, K dimensional trees, which are used in this area of case based reasoning quite a bit, quad trees which have to do with images, tries which have to do with words and alphabets and how to match strings. There are various kinds of things, all of them rely on this basic idea of discrimination, which says that you do a test and send the query or the data down a particular branch and then do another test and so on. So, the top half of our Rete Net is going to be a discrimination tree. This is how it will look. We have a working memory sitting in some location in the network, and the top half will be made up of what is called as alpha memory nodes. Alpha memories will be concerned with distribution. It will spread the tokens along different directions, and how will that happen? The working memory comes down, goes and does a test, and based on the value of the test it goes down one of these paths, this one or this one or this one or this one, as the case may be, and it will go and sit in one of these alpha nodes. So, these alpha nodes will actually store the working memory elements. So, the network itself will serve as a working memory essentially. So, I said a little while ago that the network is a compilation of the rules, but this structure that we are building also stores as the memory for storing the data essentially. Of course, the memory is dynamic, it is a short term memory that we talked about, that tokens come and go and so on. Tokens, by tokens you mean working memory elements, they come and go and so on, but the network remains the same. So, the network is like a long term memory of a problem solver, and the working memory is the short term memory as to what is the problem that you are solving, what is the data that you are addressing and things like that. So, the alpha network, the top half of the Rete network is a distribution network, and which basically discriminates on the working memory on some attribute and sends it down some path essentially. So, when you implement this, it will essentially basically mean that you take a working memory element and do a test on it and then send it to some location. But very often for the purposes of illustration, we prefer slightly more compact diagrams, and if you look at literature, there are two different kinds of diagrams that you can think of. So as I said, alpha nodes serve as a working memory for the rule based system. Everything is inside the network, the memory as well as the rules essentially. So, a working memory element is inserted at the root, it is inserted as a token. So, it is either a positive token or a negative token. Positive token if you have an add action in the rule that you are executing, or the make action. If you remember, sometimes we call them make, OPS5 calls it make, some other textbooks call it add. So, OPS5 uses the term make and remove, some books use add and delete. But for with add or make we have a positive token, and with delete we have a negative token. So, essentially if you remember the rules, it says delete this token, delete this working memory element, and then it has to go back and somehow delete it. Now, conceptually of course, what we will do is that instead of as a process of finding that token as to where is it lying in the memory, we will again go through this process of search that the discrimination tree does. And the only difference is it is a working memory element which will go through the search, so the tests which are there in the discrimination tree. The prefix of plus or minus says whether you are adding it or whether you are going to delete it. So, if you have a delete action, then we will put down a negative token and it will go and find the positive token that existed earlier and it will delete it essentially. So, the tokens, whether they are positive tokens or negative tokens, they travel down the discrimination tree, and find some location essentially. The first test in a Rete network typically looks for the class name. So, we had different class names, like we said that next rank is so much, or student name is so much, or course is so much, or whatever the class name may be. We first separate the tokens for different classes and then of course look at the attributes and so on. From the implementation perspective, the key is to figure out what is the order in which you will do the test. So, I said earlier that in the working memory as well as in the patterns in the rules, the order of attributes does not matter. So, it is not that the attribute that you mentioned first is the first one that should be tested and so on. Of course, that would be the most straightforward way of doing things, but in practice if you can figure out as to in what order to test, for example, which attribute to test next, might allow you to share more of the work than if you were to do the same test distributed in different branches essentially. So, if the same test is being done in this one branch here, one branch here and one branch there, you can move the test up in the hierarchy, so that it is done only once essentially. So, that is going to be a goal in building an efficient Rete network. So, those of you who have studied decision trees would remember that an algorithm called ID3 uses this notion of information gain to decide as to what is the next test that should be done, and the test should be such that it separates the data as much as possible essentially. And the same thing, something similar we want to do here, except that here we want to share the work that is being done by different patterns essentially. We will not go into the details of this implementation, and I hope you will think a little bit about how to do this essentially. So, the key is to sequence the test, which means which attribute should be tested higher up in the tree and which attribute should be tested lower down in the tree. And the attribute that you want to test higher up is the one which is being used in many different patterns essentially. It may be the same class this thing, but you may be testing for different things. So, student name, roll number, marks and so on. Okay. So, as I was saying, this is what you would do if you were implementing the system. You would take a working memory element, feed it to a test, and the test would direct it into different directions based on where it is going. But for purposes of illustration, we often use more compact diagrams, and we essentially eliminate drawing the test node as a separate node, and we just work with the alpha nodes that are there. And we either draw a diagram which looks like this, where the test is done at the current node. So, you can see at the top here that the test is being mentioned here, and the value of the test is mentioned on the edge that follows essentially. This is only for illustration purposes, they are easier to draw and use when we are talking about Rete Net. And supposing the test value 2 is the one that is being matched by a particular working memory element, the test is test 1 and the value is 2. And so, the node with the test value 2 will come here and sit here, and here of course, it will do another test, here it will do another test which is test 2, which is the next test essentially. So, as you can see, we have eliminated the test node and just simply remembered the working memory nodes essentially, which are the alpha nodes. An alternative way of representing the same effect is to mention the test at the destination node or at the target node. So, because the test 1 had value 2, we have kind of mentioned this whole thing here in one place, and in some sense it kind of pulls a relevant token from its parent node essentially. So, the basic idea is that the input token was at the parent node, and it has to go to one of the children, and which child it goes to is determined by the test that we are doing on that node essentially. So, these are the two diagrams that we have seen. If the working memory element passes the test, whichever test we are doing, then it moves to the appropriate alpha node in the next level, else it gets stuck on the parent node. So, you can imagine now we have this network, we put the token from the top, a working memory element, and it traverses down the network essentially, as long as it passes some of the tests which are being tested for in the network essentially. Again, remember that there can be both positive nodes as well as negative nodes. As far as finding their destination, whether they are positive or negative does not matter. What the semantics of positive and negative is that positive means that a new piece of data is being added to the working memory, negative means that an existing piece of data is being deleted from the working memory, but the location is specified by the alpha network essentially. Okay. So, the lower part of the network is an assimilation network or a consumption network. Assimilation in the sense that a rule has many patterns. It needs one working memory element for every pattern in the rule, and this lower part of the network, which is called the beta network or beta nodes in the network, they assimilate these different tokens which the rules require essentially. So, in some sense they are consuming. But you can consume tokens only if all the patterns in the rule match, and this part of the match process is done by the beta network essentially. So, beta networks have at least one parent node, more often they have more. In this diagram that I have drawn 3 beta nodes, and one of them has only one parent, the one on the right, this one here, and the other 2 have 2 parents each essentially. If a beta node has 2 parents, then it must satisfy the join condition in the way that we do join in databases as well, is that if you have a shared variable, then the variable in the 2 tokens that are coming in must have the same value essentially. So, remember that we had said that if there is a student named S and a student named S has got so many marks, then that S and S must match the same student, whether it is Neha or Sunil or Anil or Shruti, whatever the case may be. The variable which is mentioned in the pattern of the rules, remember variables are only in rules. The working memory elements themselves will have only data, only constants. So, the variable that particular rule is talking about, let us say in this example we have called it x, in the 2 pieces of data which are flowing down must have the same value. So, that obviously is, as we say, the join condition. If the join condition holds, then the 2 patterns can come together and hopefully contribute to the rule becoming ready to join the conflict set. Now, rules can be attached to any beta nodes essentially. Okay, so that's a difference. That's one difference between beta nodes and alpha nodes in this diagram that we have drawn. That if a token or a set of token reaches some beta node, and if that beta node has sufficient number of tokens to satisfy a rule, then you can say that the rule is matching essentially. In this very simple diagram, on the beta node on the right side seems to have only one condition. So, there is a very simple rule. Remember that pass rule that I had mentioned about in bridge bidding. Such rules may be something like this essentially. Now, I have drawn here 2 beta nodes on the left, and one of them is a parent of the other beta node. I could easily have written drawn this network a little bit differently, where the join is happen on 3 tokens. There is no difference in the meaning or the semantics of whichever way I construct the network. The basic idea is that there are 3 tokens which have to come together. Either they can, either first 2 of them can come together and then they can join the third token, or all 3 can come together at the same time, as shown in the new diagram. The key thing is that the variable in those arcs, these variables are associated with the paths in the network essentially, must have the same value in the tokens which are coming in essentially. Then we say that they have joined. So, here is an example of a Rete network which has some number of rules. So, it is a network for some 4 rules, and as I said, a network is a compilation of rules. So, if you had written those 4 rules, we have not said what those rules are, but you can imagine that you have written some 4 rules which resulted in this particular network being formed here essentially. And again you can see that rule 2 is a parent of rule 1, and this means that rule 2 is a default version of rule 1. Why do we say that? If you look at these 2 rules, you see that rule 2 needs only 2 patterns to match, which are coming in along. So, these red edges are the edges along which the patterns which match this rule 1 travel from. So, you can see that there are 4 paths from the root to rule 1, and each of those 4 paths represents one pattern in a rule. So, this rule 1 clearly has 4 patterns in the left hand side. It needs 4 tokens to come and match those 4 tokens. The 4 tokens will travel along the 4 paths that we have shown here in red here. So, if all the 4 tokens reach rule 1, then we will say that rule 1 is matching, and we will put it in the conflict set with the 4 tokens that have come there. Rule 2 takes only 2 of those 4 tokens. The same 4 tokens that we talked about for rule 1, rule 2 was happy with only 2 of them, and so clearly you can see that it is a default version of the rule 2. If you had all the 4 tokens, you would say rule 1 is more specific and I would like to use rule 1. If you had only 2 or 3 of those 4 tokens and rule 2 was matching, then rule 2 would still be applicable. So, rule 2 is kind of a default version of rule 1. Again, I will remind you of the 2 rules we talked about in bidding. One was to pass and the other one was to bid one no trump. Okay, so that is the idea of beta networks and alpha networks, and this whole thing is called the Rete network essentially. So, let me stop here and take a break, and we will look at some examples in the next session or next video, which will talk about some specific set of rules and how they are combined into a Rete network. Okay, so we will see you in the next session.